Assalamu alaikum. Today we will talk about section 5.3, the fundamental theorem of calculus. It is very important theorem, so that we call it the fundamental theorem of calculus. First, you know that we have two branches of calculus. The first one is differential calculus. The second one is integral calculus. The differential calculus arose from the tangent problem, and we took this in calculus 1, while the integral calculus arose from the area problem, and we took it at the beginning of this course. It seems that we do not have a relationship between the tangent problem and the area problem, but in fact there is an inverse relationship between them. That is, there is an inverse relationship between the derivative and the integral, and that relationship is given by the fundamental theorem of calculus. Let us read here. The fundamental theorem of calculus gives the relationship between the derivative and integral, and in fact that was discovered by two mathematicians, Newton and Leibniz. Now, to start this section, we will consider a function here, which is g, defined by g of x, the integral from a to x f of t dt, and the graph is given here, or let us see it here. This is y f of t, and this is our interval ab. The function g of x is defined this way: the integral from a to x f of t dt, where f is continuous. So we can see that if f of t is positive or 0, then this g of x will represent what? Will represent the area under the curve from a to x, where x is moving between a and b. Clear? If x is changing, then the area will be changing as well. So g is a function of x. So I will say g of x will be represented so far by the area under the curve from a to x. And I already wrote this information in the note. As I said, if f of t is positive, then g of x will be the area under f from a to x, where x can vary from a to b. Good. Our goal in this section is to find the derivative of such a function. The fundamental theorem of calculus part 1, which is abbreviated by FTC1. If f is continuous on AB, then the function g defined by g of x, which is the integral from a to x f of t dt, where x runs from a to b, as we said here, then this function g is continuous on AB, the closed interval I mean, and not only this, it is differentiable on the open interval AB. And also g prime of x will be what? F of x. See it here. If you differentiate, you will kill this integral operator and you will get back to f of x. Is it clear? So we can see the inverse relationship between the derivative and the integral. I mean, the derivative operator will kill the integral operator. I summarize my result here in some notes. Number 1, we can write FTC1 as d by dx, the integral from a to x f of t dt, when f is continuous, as what? The derivative will kill the integral, as I said. Then you just put this x instead of this t. So the answer will be f of x only. Good. Note number 2, g of x, which is defined by the integral from a to x f of t dt, is a function of x, not a function of t. What is the reason? We said this here. If x is changing, then g will be changing. I mean, the area will be changing. So it is a function of x, not in t. We need this in a later question. So let us start by the following exercises. Differentiate g of x, which is the integral from 0 to x root 1 plus t square. Let us recall the theorem here. See here, we just substitute x instead of t when we have f to be a continuous function. So it is continuous function. Since f of t, which is the integrand here, 1 plus t square, is continuous, then by fundamental theorem of calculus part 1, we have the following: g prime of x will be d by dx. That means differentiate the integral from 0 to x 1 plus t square. We apply the theorem. Just put x instead of t. The answer will be just root 1 plus x square. I repeat, the derivative will kill the integral, and you just put this x instead of this t. Common mistake, usually the students will differentiate the inner function. This is not correct. When you differentiate, you kill one integral, so that's it. You get back the original function f. So just put x instead of this t, and that's it. Part B says differentiate g of x, which is the integral from x to 5t cosine t dt. What is the difference between this part and part A? We had what? X upstairs and a number downstairs. Here we have the other way around. So what shall we do to put it in this form? You just use the properties. You just switch them and you put minus. So the solution will be written here. G of x will be minus the integral from 5 to x t cosine t dt. Now we have this integral in this form, so we can use the theorem directly. So I will write the answer directly. G of x will be what? Minus for sure, because we can take it outside the differential operator. To differentiate this, put x instead of this t and this t. So the answer will be x cosine x. That's it. Now we see part C. It says differentiate g of x, the integral from 1 to x to the power 4 secant t dt. Well, what is the difference between this part and the previous ones? We can see that we replace x by a function of x, that is x to the power 4. What shall we do to solve this exercise? Well, we need to combine this theorem with the chain rule. Just let us recall this from Math 101 quickly. If you have a function h of x which is equal f of g of x, how can we differentiate it? As we done this in Math 101, you differentiate the outer function f prime of g of x. Then you multiply by the derivative of the inside function. So this is the chain rule. Just to understand, let us take a quick example. Assume we have y equals sine x. Then what is y prime? This is cosine x. Now, if you replace x by x to the power 4, what shall you do? You will use the chain rule. You differentiate the outer function, that is cosine x to the power 4, and do not forget to multiply by what? 4x cubed. That is the derivative of the inside function. This is very important. Let us see part C again. As we said, we need to combine it with the chain rule. So directly I will say g prime of x will be secant of x to the power 4. You substitute this x to the power 4 instead of this t. And do not forget to use the chain rule. I will write it here, d by dx, x to the power 4. And I will write using the chain rule. The derivative here will be 4x cubed, and write this secant x to the power 4. That's it. We are done with this exercise. Now we will see part D, where we will change this constant by a function. That means the integral will be from a function to a function. That is the most general case of this question. Part D, he said differentiate this function, which is the integral from 5x to x cubed sine t. How can we do this? As I said, this is the most general case. We need to put it in this form using the properties of the integration. G of x will be the integral from 5x to 1, for example, number sine t dt, plus from this constant 1 up to x cubed sine t dt. And we said this maybe last time. We said you can connect this number 1 with this number 1. So you will get the integral from 5x to x cubed. Now, this integral is in the standard form, but this one is not in the standard form. So what shall we do? We just multiply by minus this integral only. So we get the integral from 1 up to 5x sine t dt, plus the integral from 1 to x cubed sine t dt. So g prime of x will be minus, you just substitute 5x instead of this t, sine 5x, and do not forget to multiply by the derivative of the upper function plus the same here, you will get sine x cubed times, do not forget the derivative of the upper function, which is what? 3x squared size. Any questions here? Since we do not have any question, let us see the general version of FTC1 together and we will illustrate by more examples. Here we have a question. He said, I didn't understand the target of this theory. You will understand why. First, we will differentiate functions of this form, because usually in the application in physics or chemistry, you will have functions of this form. And sometimes we are interested to differentiate that function, to find the maximum, minimum, critical numbers, etc. So what shall we do? We need a theorem. In fact, this theorem is called FTC1. Another application will be the part 2 of this theorem. You will see it soon. Now let us see the most general case of FTC1. He said here, if f is continuous and g and h are differentiable functions, I will give you the reason for these conditions. If you need to differentiate this function defined by the integral from a function g of x up to h of x of f of t dt, the formula is given here, but let us understand it. First, you put this h of x instead of this t to get f of h of x times you differentiate the upper function to get what? H prime of x. Then you put a minus sign. Same idea, you substitute g of x instead of this t to get f of g of x, and do not forget to multiply by its derivative. I wrote these details here. Substitute by the upper function, differentiate it, minus substitute by the lower function, then differentiate it. I didn't tell you the reason for having these conditions. For the continuity, recall from fundamental theorem of calculus 1, we need f of x to be f of t to be continuous on AB. So this is clear. Why do we need the differentiability on g and h? This will be clear because in the formula we will have h prime of x and g prime of x, and this is valid if you have g and h to be differentiable functions. Great. Let us see the reason for having this minus. Let us go back to the previous question. You see here, first you substitute by the upper function, you get sine x cubed. We have it here. Then you differentiate the upper function, that is what? 3x squared. Then you put minus. Substitute by the lower function, which is sine 5x, then differentiate this 5x to get 5. The minus sign comes from what? Switching the boundaries. Is it clear, ya shabab? Here we have a question from Abdullah. He said, is it like b minus a? I didn't understand what you mean by b minus a, but in that section we were interested to integrate constant function from a to b dx, and the answer was cb minus a. But today we need to differentiate a function of this form from a number to a function. Good. Now I will solve a question, then I will give you another one to try it. Let us go to part E. He said differentiate this function g of x, the integral from cosine x up to 5x cosine t squared dt. Well, we will use the formula directly, or you can use the properties as we said before. You will split the integral from cosine x up to a number plus that number up to 5x, and you proceed as in the previous exercise. The answer here directly will be what? G prime of x, substitute by the upper function inside instead of this t, I mean. So it will be cosine 25x squared. And do not forget to differentiate what? The upper function, which is 5x. Minus, substitute by the lower function. You will get cosine, put t equal to cosine x. So you will get cosine square x. And do not forget to differentiate the lower function, which is what? Minus sine x. And this is the final answer. Common mistake in the concept. Usually the students will differentiate the inner function. Please do not differentiate the inside function. Here, thank you very much. Here we do not have x, it is 5 only. Thank you very much. So once we differentiate it, we get what? We get 5. Good. Now I will give you 1 minute only to solve this exercise, and if you see the recording, please stop the video and solve this exercise. Now time is up. The answer is given here. I think this is not difficult. If you put x squared instead of this t, you will get x to the power 4. Differentiate the upper, you will get 2 minus. Substitute by the lower one and differentiate it, you will get 1. Let us recall this question. You remember when we differentiate this, we ignore the number 1. In fact, the general version will help us. Let us see it. If you apply the general version here, you will get what? You will get secant x to the power 4. Then you differentiate upstairs, you will get 4x cubed. Minus, substitute by 1, you will get secant 1. Differentiate the number 1, what do you get? You will get 0. So this is the reason for ignoring the constants. Good. Now we will go to more exercises. Now if you see the recording, please stop the video and solve these questions. Part A. He said, find the slope of the tangent line to the curve y equal 0 to x cubed root t plus e to the power t dt at x equal to 2. This is a very simple question and it comes from all the exams. Well, first of all, we need to find the derivative. What is y prime here? It is given by Ftc1. You just substitute by x cubed instead of these t. So here you will get what? You will get x cubed plus ex cubed and differentiate by the upper function, which is what? 3x squared. And no need to substitute by the lower number here, which is 0, because if you differentiate, you will get 0. Now that's it. The slope of the tangent line will be what? Will be y prime evaluated at that number, which is 2. So here you will get what? 8 plus e to the power 8 and multiply by what? 3 times 4, that is what? 12. So we can write this 12 here. Part B, he said if x sine by x equal the integral from 0 to x squared f of t dt, where x is positive and f is continuous, we need to find f of 4. First, this question is taken from the problems plus. These questions are high level questions and you can find it at the end of each chapter in the textbook. He said we need to find f, then we substitute by 4. Where is f? It is inside the integral. So how can we reach to this f? You need to break this wall. I mean, you need to break this integral. How can you do it? You need to differentiate. For sure, you need to differentiate this side and this side. Differentiate both sides. Note, the left-hand side will be differentiated using calculus 1. But the right-hand side will be differentiated using math 102, calculus 2. So the derivative of the left-hand side will be what? Using the product rule, differentiate the first, keep the second one, plus the other way around. Keep the first, differentiate the second one, which will be cosine by x, and do not forget to multiply by which comes from the chain rule. I hope you remember this. Equal, the derivative of this, we learned it today, it will be f of x squared. We substitute, then do not forget to differentiate the upper function, which is what? Which is 2x. Now, how can we proceed? He said we need f of 4. Usually the students will substitute by 4. If you substitute here, you will get what? F of what? F of 16. But in the question he said, I need f of 4. So what shall we do here? The trick is simple. You just equate x squared by 4. Solve x squared equal to 4, where x is positive because this is a condition. For sure we will get x equal to 2. So I will say put x equal to 2 in the last equation, and here's the solution. Sine 2 pi will be what? Will be 0. Cosine 2 pi will be what? Will be 1. And this is 2, so you will have 2 times 1 times pi equal, put 2 here, you will get f of 4 times 2 times 2, that is what? Times 2 will be 4. So what is the answer? It will be f of 4 equal 2 pi over 4, and this is simple, pi over 2. So this is the answer for this exercise. Now I will give you 1 minute to solve this exercise, and if you see the recording, please solve this exercise. Okay, time is up. The answer is 5. I hope you get it. Now we will solve part D. He said find the limit when x goes to 3, the integral from 3 to x sine t dt over x minus 3. Well, it seems that this question is taken from Math 101, but in fact it is in Math 102. Let us substitute by 3 to see the idea. Here you will get the integral from 3 to 3. And what is that? That is 0 over. Put 3 downstairs, you will get 0. So we get 0 over 0 case. Here we need to use Velobiter rule. So this limit will be the limit when x goes to 3. What is the derivative upstairs? We learn it today. You just substitute by x. You will get sine x over x. Differentiate x, that is 1. And ignore this number 3, because if you substitute by it, then you differentiate it, you will get what? You will get 0. Now differentiate downstairs, you will get what? You will get 1. And what do you think about this limit? Please answer me in the chat. Usually the students will say 1, but this is false. The correct answer is what? Sine 3 over 3. What is the reason? Be careful. X goes to 3. If x goes to 0 like this, the answer for sure, yes, it is 1. But be careful here. Now let us see part E. This one is very interesting. He said, if f of x equal the integral from 1 to x, x squared sine t squared dt, find f prime of x and also find f of 1. First of all, do you notice something here? There is something different here. We have x squared inside and we have t. I mean, we have two variables, that is x and that is t. Here in the previous exercises, make sure that you can see only the variable t. If you have x squared, you need to take it outside using the properties of the integral first. First, I will write the integral from 1 to x sine t squared dt and take x squared outside. I repeat, why can we take x squared outside? Because the integral depends on what? T. So anything other than t, you can take it outside the integral. See here, this is a function of x. And what about the other one here? We said this before in one of the notes. It is function of x. It is function of the upper limit. See here the note again. We said this. G of x, which is defined this way, is a function of x. It is very important in solving this example. So you have a function of x times another function of x. How to differentiate this function? For sure you need to use the product rule. F prime of x will be, differentiate the first, that is 2x, keep the second, that is the integral from 1 to x sine t squared dt, plus the other way around. Keep x squared, differentiate the second one. It will be sine x squared, right? And differentiate the upper limit, which is 1. And as we said before, no need to substitute by 1, because if you differentiate, you will get what? You will get 0. So this is f prime. This is part of the question. He said, find f prime at 1. Just substitute. If you substitute here, you will get what? 2 times the integral from 1 to 1 sine t squared dt, plus substitute here, you will get 1, 1, and here you have sine 1. What is this? Yes, you are right, this is 0 using the properties. So what is the final answer? It will be sine 1 only. That's it. Now, if you see the recording, please stop it and try these questions. I will not solve them. Okay, good. Now we will see the fundamental theorem of calculus part 2. Before we start this theorem, let us read together. The following theorem will provide us with a simple and quick method for the evaluation of integrals. Remember, in section 5.2, we were able to integrate specific types of functions, that is, polynomials of degree 3 or less. For example, this function. And we use the definition limit of summation f of xi delta x. And at that time, this question is taking lots of time to solve it, because we use what? We use these formulas: summation of I squared, I cubed, and constant term. What is the reason for having this restriction? polynomial is of degree 3 or less? Because degree 3 will give you summation of I square, I cubed, I constant only. What about if we have other functions? For example, polynomial is degree 4. In this case, you need to look for formula for I to the power. Find it in the internet if you wish. But from now and on, we will not go to the internet and find formulas for I to the power 4. We have a very important tool that is called Fundamental Theorem of Calculus Part 2. Let us read it together. This theorem is abbreviated by FTC2. It says if f is continuous on AB, this is very crucial condition. Be careful. If we have this condition, then the integral from a to b f of x dx is nothing but capital F of x. That means give me an antiderivative of small f and evaluate from a to b. So if you evaluate, you will get f of b minus f of a. As I said, capital F is an antiderivative of f. And this means that if you differentiate capital F, you get back to f. i.e., if you differentiate the antiderivative, you will get back to the original function. This is very important, so I will repeat it again here. The integral from a to b f of x dx is given by capital F of x, and you can use this notation. From a to b, you evaluate at the end point, which is f of b minus f of a. This result is wonderful, ya shabab. Why? Because instead of doing limit of summation stuff and using summation of I squared, etc., you just give me an antiderivative, then you evaluate by 2 points. That's it. You will get the answer in one line, provided that the function f is continuous. Also here we have a small note. He said other notation for f of x from a to b is to use what? Is to use this bracket, or you use just a line, or you close it from both sides. These things will be used. So let us see exercises. Now we see question number 3. I will solve part A and you need to solve part B yourself. He said here, find the area under the curve y equal x squared from 0 to 1. You remember this question? We solved it in section 5.1. The answer there was 1 over 3. Let us recall. This is y equal x squared, and we are interested in this region from 0 to 1. So this is our region of interest. This is y equal x squared. The area will be exactly the integral from 0 to 1 x squared dx. What is the reason behind this? We said this in section 5.1. If the function is positive, that means above the x-axis, then the integral will be directly equal what? The area. And what is this integral? Using this fundamental theorem of calculus part 2, just give me an antiderivative, that is x cubed over 3. You just add 1 into the exponent and divide by the new exponent. Evaluated from 0 to 1. Substitute by 1 will give you 1 over 3. Minus substitute by 0 in this function, you will get 0. So the answer will be what? 1 over 3. That's it. Please try part B. I will give you 1 minute. The answer for part B is 1. Good. Now we see part C. He said integrate this function from 1 to 3 ex dx. As I said before, you cannot find this using the definition yourself, because you will get unfamiliar form. That means other than we are limited by summation of I squared, I cubed, etc. So you cannot do this unless you use a computer. So what shall we do? We will use fundamental theorem of calculus part 2. What is the answer here? It will be the antiderivative of e to the power x, which is e to the power x directly evaluated from 1 to 3. And what is the reason for putting this? Maybe I forget this in the last exercise. Since f of x, which is ex, is continuous on the closed interval 1 to 3. This is very important. This is a condition given in the fundamental theorem. See it here again. We need the function to be continuous on the closed interval. Substitute by the upper limit, you will get e3, minus substitute by the lower limit, you will get e1. So this is the answer. Now I will give you a small note quickly. Usually the students will say, why don't you add c, the constant, in the antiderivative? Well, remember, he said, give me an antiderivative only. Give me one of them and that's it. This is the integral from 1 to 3 e to the power x dx. Well, you find the general antiderivative, which is e to the power x plus constant. You evaluate from 1 to 3. Then, if you evaluate at 3, you will get e3 plus constant c, minus evaluate at 1, you will get e to the power 1 plus constant c. Clearly, you can see that this constant c will cancel this constant c. Then the answer will be e cubed minus e to the power 1. So it is the same story. Part D, he said evaluate this integral from minus 3 to minus 1 over x dx. First of all, before we evaluate the integral, we need to check whether this function f of x equal 1 over x is continuous on this interval from minus 3 to minus 1 or not. Clearly, the discontinuity here is appearing at the 0 of the denominator, which is x equal to 0. Fortunately, this 0 is outside our interval, so it's fine to apply FTC2. If you didn't see this clearly, let us see the graph here. Clearly, this is our interval minus 3 to minus 1, and the function is continuous there. See here, the 0 is outside our interval. So I will write, since f of x equal 1 over x is continuous on minus 3 minus 1, what is the antiderivative of 1 over x? Clearly, this is ln absolute value of x evaluated from minus 3 to minus 1. Substitute, you will get ln minus 1 minus ln absolute value of minus 3. Simplify, this will be ln 1 and that is 0. Minus, simplify this, you will get minus ln 3, and the final answer is minus ln 3. Notice that we get a negative number here, and that is fine. Why? Because the integral will represent the net area. Maybe we can see it clearly from here. The function f of x is below the x-axis. For sure, this integral will be negative. Part E and F, please try them. Part G, he said, what is wrong with the following calculation? The integral from minus 1 to 3, 1 over x squared. We will complete the question together to understand. 1 over x squared can be written as x to the power minus 2 dx minus 1 to 3. He said to integrate this, just give me an antiderivative, that is x to the power minus 1 divided by the new exponent, which is minus 1. Evaluate from minus 1 to 3. He said put 3, you will get 1 over 3 by minus 1, that is minus 1 over 3. Minus, substitute here, you will get minus 1 to the power minus 1, that is minus 1 over minus 1. The answer will be minus 4 over 3. He said, what is wrong with the following calculation? What do you think? The mistake comes from here. Remember the condition in the fundamental theorem of calculus part 2. We need f to be continuous on the closed interval. Do we have it here? No, we have a discontinuity at 0, which is inside the interval. So the answer will be written here. F of x, which is equal 1 over x squared, is not continuous at x equal to 0, which is inside our interval. In this case, thus, FTC2 is not applicable. In fact, the integral from minus 1 to 3, 1 over x squared, does not exist. More on this situation, more in section 7.8. Next question, he said evaluate the integral from 0 to pi f of x dx, where the function equal sine x f x between 0 and pi over 2, and it is equal cosine x f x between pi over 2 and pi. Well, here we need to integrate piecewise functions. The first step is to write the number line as follows. From 0 to pi over 2, we have the function sine x, and from pi over 2 to pi, the function is cosine x. So we split the integral. The integral f of x from 0 to pi will be the integral from 0 to pi over 2. What is our function? It is sine x, plus from pi over 2 to pi, our function is cosine x dx. And these are simple integrals. We will do them by fundamental theorem of calculus 2. What is the antiderivative here? It is minus cosine x evaluated from 0 to pi over 2 plus the antiderivative here is sine x evaluated from pi over 2 up to pi. Substitute by pi over 2, you will get what? You will get 0 minus, do not forget we have to put a bracket. Substitute by 0, you will get minus cosine 0, that is minus 1. I repeat, this minus comes from the subtraction. I mean evaluation at B minus evaluation at A. Plus, substitute by pi, you will get 0 minus, substitute by pi over 2, you will get 1. If you do this computation, for sure you will get 0. I wrote here a note. The function f of x is integrable. See theorem number 1 in section 5.2. Why did I write this note? Well, if I ask you, is this function continuous on the interval 0 to pi? In fact, no, there is a discontinuity at pi over 2, which is jump discontinuity. Check. What is the limit when x goes to pi over 2 from the right? It will be cosine pi over 2, that is 0. If you evaluate the limit when x goes to pi over 2 from the left, it will be sine pi over 2, which is 1. So the limit from the right is not equal to the limit from the left. That means we have a jump discontinuity. Well, if we have a jump discontinuity, can we still integrate the function? In fact, the answer is yes. And here's a theorem number 1 in section 5.2. Let us recall it together. It says if f is continuous or f has only a finite number of jump discontinuities, then f is integrable on AB. Good. Question 4, part A. He said evaluate the limit when n goes to infinity summation of I to the power 5 over n to the power 6. Method number 1 is to look for a formula in the internet for I to the power 5, plug it back, evaluate the limit, and you are done. But we will not proceed with this. Instead of that, we will change this limit of summation to an equivalent integral, then we evaluate that integral. Let us recall the following choice, and as I said many times, we will choose this simplest choice, which is delta x to be 1 over n and xi to be I over n, and the reason for this is to have the integral from 0 to 1. Let us take n from the denominator and write it as this, 1 over n, then write I to the power 5 over n to the power 5. Next, let us write the limit of summation, 1 over n. This fraction can be simplified this way, I over n all to the power 5. And this is very nice. Why? Because we will choose this to be xi and this is our delta x. Now the integral will be from where to where? From 0 to 1, as we said. Delta x will be dx, and this is our xi, so we'll get x to the power 5. And now this is very simple exercise by using the fundamental theorem of calculus part 2. One antiderivative will be x to the power 6 over 6, evaluated from 0 to 1. Substitute by 1, you will get 1 over 6 minus 0. So the answer at the end of the day will be 1 over 6. If you need more questions, please stop the video and solve the rest from part B up to E. Thank you very much. This is the end of section 5.3.